the next law is actually interactive response time law. And this was actually designed more for time sharing systems, where one system was shared by many, many users. Something similar may apply now to thin clients. And so from that point of view, basically, we still use the same central server model. Now, I assume everybody knows what is a central server model, right? In the central server model, the CPU was the central server, and everybody went around to different devices through CPU. So one of the devices that you go to is your terminal, and your think time is Z at the terminal. The response time is R, which means the time to leave the terminal and come back to the terminal is R. So the total cycle time is R plus Z. Right? Z is the think time, that is the time the job spends at the terminal, and R is the time that it spends in the system. So R plus Z. Now, if you observe it for T seconds, then you will have generated T upon R plus Z requests. And therefore, the system throughput would have been that many requests divided by T times the N terminals, because there are N terminals. And therefore, the system throughput would be N upon R plus Z. Very simple derivation. Without any assumptions again. So based upon this, we can calculate the response time. Response time is R is equal to N divided by X minus Z. And this law is called interactive response time law. An example is this system that we have been doing it for a long time. So here the Z is 18 seconds. There are 17 terminals, and each of them takes 18 seconds. Now this is this could be the mean, or this could be whatever basically. So 18 seconds is the time. We don't know what the distributions of any of these things. And here the total time at the CPU is 5 seconds. Total time at the disk A is given, and V is given like as follows, right? So anyway, so all we need is for response time is N upon X minus Z. If suppose you are given that X is 0.1963, however it is calculated, then you can say the response time is 17 upon 0.1963 minus 18, which comes out to 68 seconds. All right. So given the throughput, system throughput, you can calculate the system response time. And since the system response time is same as what we obtained before, that means in some cases you might know the response time and you need to calculate the throughput. But this is the relationship between the two. So that finishes the operational laws. And by now, after having done the homework, at least some of the symbols would become familiar to you. V for visit ratio, S for service time, D for total demand, X for throughput, Z for user think time, and N for the number of years in the system. Now we are going to use these same symbols throughout the rest of the queuing theory system, right? So you just have to get used to those. And the only assumption we have made in any of these operational laws is that job flow balance. Job flow balance means input equal to output, means nobody dies in the system. Very easy to remember. We are not assuming anything about the distributions, independence, nothing like that. All right, operational laws. And the laws, there are 5 laws that we have learned so far. Utilization law, U equal to XD. Force flow law, X is equal to XVI. XI is equal to X times VI. Little's law, QI is equal to XI RI. And response time law, R is equal to RI VI. And the last one is interactive response time law. Here we are assuming that this user is basically continuously working on the system. And what happens is when the response comes back from the system, says that, okay, your previous request is done, then it has to think about what to do next. Okay, that is called the think time. And so, for example, if you were compiling a program, the compilation came back and gave you some errors. Now you have to fix those errors. Then it came back, no errors. Then you have to execute that program. then it executed the program but ran with an error. Then you're going to go back and edit the program. So these are things that you could not really do before. I mean, you could not, these steps you know only after the response comes back, then you have to think about the next step. So that is called the think time. So in our system today, we don't use, the problem is this model does not apply to the current Windows systems because of what? If you have a single computer and a single user, what is the difference between this model that was given here and the system that we have? Can anybody think of a queuing model for a laptop? Yeah, so the users are not just dedicated in the sense that here, as soon as the job comes in, the user does that. You know, in our current system, when I'm doing debugging, also I am doing emailing and I'm also doing something else. So when the compiler comes back, I'm still not thinking about the compiler, I'm thinking about the email. Right? So in the current laptops, the user has a queue. Right? So this model, which is infinite server model, does not apply. Right? So basically what will happen in the current system, basically there is only one user, so n equal to 1, but there is a queue behind it. It's very similar to, in some sense, like the disk and everything else. The user has also become one of the things where there's a queue and then the queue is, all right? So that would be a different model. But in the old systems, the user didn't have the queue. And many users shared the same system. So that is another thing is now we don't share the system that much. Actually, you might share if you are doing something in the cloud or if you are doing something, you know, in the data center and things like that. So you have to really prepare the right model and then apply these rules. Now the operational quantities are VI, SI, DI, G, and N. And you should memorize basically that the total demand is service times per visit times the number of visits. So DI equal to SI, DI. That is something that you don't need to look at the book. You might need to look at the book for many of the other laws, but these are something that, you know, basically you should know. And so now we are going to apply all these laws to this system. This is an example, right? So in this example, actually we have done most of this example anyway. Let's see, this is different than the before. 80 times 50, 30, 10 times 30. Okay, I think we have finished this example already, but we are just going to do all of them one more time just for review purposes. So first law is UI is equal to XI, SI, XDI. So first what we are given here is that user A, sorry, not user A, the device A utilization is 75%. That is what we are given. Somebody measured utilization and said 75%. And the Q at disk A is 2.41. Somebody measured that and said that. And QB is 1.21 and QC, CPU, QC is 5 seconds. No, it's not 5 seconds. Number of jobs in the queue is 5. Okay. So somebody measured these 3 queues and found one utilization. Based upon this, what can we say? All right. So we wrote down those formulas, and this is the kind of thing that you will get in the final exam. You will be given some things, and you will have to determine the rest of the things. So these are the quantities, and some of them are given, and some of them are derived. So utilization law is U is equal to XI SI, which is same as X times DI. Now, we don't know any D's here, but we know at least one U. Since we know one U, we can do something with that U. So X is equal to UA upon DA. So we can calculate the system throughput because we know the utilization of A and we know the demand, total demand on A. Actually, that was not listed here, but that was given before. D1 and DA, DB, and DS. So this is DC, this is DA, and this is DB. So DA was given there. So based upon that, we can say X is equal to so much. Once we get X, we can calculate UC and UB. Now we go to the next law. Next law says XI is equal to X times VI. So now we know X and we know all the visit ratios. So we can calculate XI's, all of them. So you can calculate XA, XB, XC. Third, Little's law. QI is equal to XI RI. Now we know all the X's, we know all the Q's, so we can calculate all the RIs. Alright? So RA is equal to QA upon XA, RB is equal to QB upon XB, RC is equal to QC upon XC. So we calculate 3 response times. The general response time law, it says R is equal to sigma of RI VI. We know all the R's, we know all the V's, and therefore we can calculate the system response time. Once we know all the system response time, then we can calculate the next one is interactive response time law, which says R is equal to N upon X minus Z. Now we know R, we know Z, we know N, so we can calculate X. Actually, in this case, X we already knew. So all we can do is, we know all of the variables, we can just verify that everything is correct. So we calculate R all over again, N upon X minus Z, and it comes out the same as before. So it just shows that we applied the previous laws correctly. So basically, you need to just know all 5 laws, and you will be given some of the quantities, and then you'll have to calculate the rest of the quantities, somehow figure out how you can get what. All right, so then there is a homework which exactly asks you to do the same thing, apply all the 5, 6 laws to this system. Some quantities are given, the rest of them. And in fact, the good thing about this particular homework is that everything is already written in front of you. So all you do is just go line by line by line. You don't even have to think about what law to look for. Right? It's already given. So just fill up all the blanks and you will be done with that. So now the new topic is bottleneck analysis. And this is again very important part of the whole performance analysis and queuing theory. As I said, that really the system performance is determined by the bottleneck. And so let's see how it works. First of all, we know that utilization is proportional to DI, because the utilization law says, the forced flow law says, or actually it was the utilization law combined with forced flow law said UI equal to XDI. X is constant, so therefore UI is proportional to DI. So basically the device which has the highest demand has the highest utilization, and therefore all we need to do is just calculate the demand, and we know which one is the bottleneck. And we can improve the throughput by just improving the bottleneck. And so let's try to do that. And based upon that, we can write some bounds. Basically, the system throughput cannot be more than these quantities. This is called asymptotic bound. And I'm going to tell you how this came about. Throughput cannot be more than that, and the response time cannot be less than this. Based upon simply the observation that bottleneck determines the system throughput and the response time, one could come up with a formula which says the response time cannot be less than this, these 2 lines here, and these 2 lines here. So this line, 1 upon D max, is this line, horizontal line. Regardless of the number of jobs in the system, throughput cannot be more than that. And this line, N upon D plus Z, is this line here. And so basically, the throughput cannot be more than that value. So throughput has to be, so the actual graph is somewhere here. We cannot derive that law yet, and that exact thing yet, but we are very close to it. Just with the operational laws, you can draw 2 lines. They say that the throughput cannot be more than that. And good thing is that you can, me is where these 2 lines meet. Okay, which means these 2 terms are equal. And similarly, on the response time has to be more than capital D. Capital D is the sum of all the DIs. Okay, so this is the response time, the horizontal line. And N times D max minus Z, this is this angle line, this line at an angle. And so response time cannot be less than that, those 2 lines. And the knee is at the point where these 2 lines meet, and that point would be exactly the same as that knee on the throughput. So you can calculate the knee by either of the 2, set this equal to that or set this equal to that. So now what you can do is, given some of these values, and actually there are not that many values here, N, D, and D max, N, D, Z, and D max. Those three values, you can calculate the knee, you can calculate the minimum throughput, or maximum throughput, and the minimum response time, and you can make lots of decisions without, just based on the back of the envelope, without going through lots of queuing theory. All right, now let's see how the system comes about. The proof basically based upon three things. First of all, utilization of any device cannot exceed 1. That puts a limit on the maximum obtainable throughput. So the bottleneck device has the highest utilization, and it will be 1 in the worst case, in the highest throughput case. And the response time of system with any users cannot be less than system with just one user. All right, if you have 2 users, obviously response time will be more than 1 user. If you can derive the formula for 1 user, then you can get some lower bound on the throughput and the response time. And the third observation is the interactive response time formula can be used to convert these two into the other limits, because this formula applies to all cases. If we can just solve these 2 cases, then we can apply this one to get those. So let's just do that. First of all, the bottleneck device throughput equal to utilization equal to UB equal to X times D max. X is the system throughput, and D max is basically the bottleneck device's demand. And therefore UB is equal to X times DB, or and therefore this has to be less than 1. That means X D max has to be less than 1. That means X has to be less than 1 upon D max. So you can draw a horizontal line, 1 upon D max. System throughput can never be more than 1 upon D max. Similarly, the system response time has to be at least equal to all the demands on the system, on all the devices. So if there is only 1 user, it will go to device 1, 2, 3, 4, 5, M devices. And therefore, the response time with 1 user is equal to capital D. Capital D is the sum of all the demands. And therefore, you can draw a line here that the response time cannot be less than this line with any number of users. So we got 2 very easy limits, right? Now we use the third thing, which is that the R is equal to N divided by N divided by X minus Z. And that means that the Rn, just put subscript Rn here, equal to N upon Xn minus Z. And if we put for Xn, we know that the Xn has to be less than D max, 1 upon D max, remember? Xn has to be less than 1 upon D max, and therefore Rn has to be greater than N times D max minus Z. Second thing we can say from here, this formula is that the Xn is equal to, bring it there, N upon R plus Z, N upon R sub N plus Z. And since we know that the Rn has to be more than capital D, and therefore Xn has to be less than N upon D plus Z. So we got 2 more limits on the throughput and response time. This limit is that one. Sorry, this limit, throughput limit is that one, and the response time limit is this red line. Red line and the horizontal red line gave us this red line and the response time. This blue line in the throughput came about because of the blue line here in the response time. Right? First we derived the 2 horizontal lines, and then this blue gave us that blue, and this red horizontal gave us this red. So now we have limits which says that the response time has to be more than that, and this one says that the throughput has to be less than this. This formula is basically saying the response time for n users is this much. We just didn't put R sub n. Similarly, this X is for n users. So X is a function of n. So for memory purposes, for memorization purposes, we just remove those n things here. But we remember that R is equal to N upon X minus Z. But this X is for n users, this R is for n users. Right? So now we are explicitly putting that n just to be, so that, we can show the whole graph. And this is a very powerful result. Believe it or not, so simple, but very powerful, because you don't really need to know the exact graph for many systems. Now, this doesn't have to be a time sharing system or anything else. In many queuing systems that you have, you can do similar things and draw lines which show you the bounds without doing too many. Now, there's no assumption, by the way, here. We are not assuming exponential. You're not assuming anything about anything. All we are assuming is one thing. And can anybody remember what was that one thing? What is one assumption in the operational analysis? Job flow balance. And that is very easy to verify. And all it says is nobody dies in the system. Right? There is no packet loss. There is no job loss. As long as there is no loss, all of these laws applies. All of these laws apply. And you can derive similar bounds for your system. And not only that, you can derive, you can explain it to anybody. That's the biggest thing, is that you don't have to go through, oh, this is exponential, and therefore here's the exponential formula, and here is integration, and here is differentiation. This is so simple, right? Now, so now the optimal operating point. You don't want to operate this system here, below the knee. Why? Because you paid for the system and you want to make maximum use of it. Here it is underutilized. Right? And you don't want to operate the system on this side beyond the knee. Why? Because you are wasting your people's time. The response time goes up. You want to get the minimum response time and the maximum throughput. And that happens only at the knee. So basically what you want to do is you want to get to the knee, and that you can get by putting those two terms that you had before in the two asymptotic bounds equal. So D equal to N star D max minus Z will give you N star, the knee point, equal to D plus Z upon D max. So based upon that, you can calculate what is the number of users that is optimal, and then you can do what we call capacity planning. So if you're buying a system, buy it so that you can support the number of users that you have, or you limit the number of users to N star. Now, there is one more thing actually. Everybody knows what is a power. Have you introduced the term power in the matrix when we were talking about the matrix before? Chapter 2 or 3 or 4. Right? Chapter 2, 3, 4. And basically, power is the ratio of throughput to the response time. So if you divide throughput by the response time, you can get a asymptotic bound on that too. Basically, in this part, throughput divided by response time. Response time is constant, and therefore power is going to go linearly up. In this part, where throughput is constant and the response time is going linearly, you're going to have 1 upon X kind of graph here. 1 upon N kind of graph here. So this is the power, and the power is maximum at the knee. Again, all these knees are same. So you can calculate the knee from the throughput, you can calculate the knee from the response time, you can calculate the knee from the power. Knowing this helps, because if you have a system where you want to maximize the throughput dynamically, that means you want to do it while you are working on the system. One of the strategies you can do is you could just calculate the power, and if the slope is positive, increase the load. If the slope is negative, decrease the load. Right? And I wrote it down because this was a case, exactly the case that happened in one of the systems that one of the students was working on and this year. Okay, this is not an old system. And they didn't basically know as to what the optimal point is and how to use this thing. So I wrote it down explicitly that basically all you have to do is calculate the power. That means you're calculating throughput, response time, and everything else, right? But calculate the ratio of the two, and if the slope is positive, you can put more jobs in the system. And if the slope is become negative, you just go. So basically what you will be doing is you will be just hovering around this area. All right, let's take an example for the asymptotic bound. This is the same system that we had before. So all we need to do is write down all the things that are given. So dA is 4, dA is this A, 80 times 50 is 4. dB is 3, 100 times 30 is 3. And Z is 18. And D CPU is 5. It's already given. So total D is sum of all DAs. Total D is 5 plus 4 plus 3 equal to 12. D max, out of all these D's, the maximum is 5, therefore D max is 5. And so we can use the asymptotic bound law, which says Xn is less than minimum of n upon D plus Z, comma 1 upon D max. That means minimum of n divided by D. D is 12 plus Z. Z is 18. 12 plus 18 is 30. N upon 30, comma 1 upon 5. D max is 5. So that is the formula for throughput bound. For response time, it has to be it has to be more than the maximum of these two. Maximum of D, capital D is 12. And N D max is 5. So 5 times N minus Z is 18. So we know basically these bounds are as a function of N, where N is the number of users. We can plot them. So the plot will say that the throughput has to be less than these two lines, and the response time has to be more than these two lines. And on this graph, what I have done is I have also plotted the exact solution, which I haven't taught you, but that is the next chapter. Right? So I have plotted the exact solution. You can see that the exact solution doesn't give you too much more information. It does give you exact answer, but I will tell you what is the problem. I mean, why you won't want the exact answer. But this one gives you almost the same thing that you need, because see, it's very close. Yeah. Exact solution means either they will go through exponential distribution assumption and then derive exact number. These are bounds. All these are saying is that this throughput has to be less than this. But somebody asks you, what would be throughput? You say, well, I don't know that, but it has to be less than this. Right? With MVA, which is coming up, and if it makes them happy, which it makes a lot of people happy, and it makes a lot of reviewers happy if you have a paper, is that you did the exact calculation, after making certain assumptions. Remember, in the bounds, we didn't make any assumptions, right? But if you make the exponential assumption, which is actually approximate to begin with, so this so-called exact solution would be approximate. But that is what academics and the reviewers want to see. Otherwise, they will say this is trivial, right? If you want to make it complex, then here's the formula. So we'll teach you that MDA, which is the exact solution, and exact solution is this. And the knee is at 12 is equal to 5 and star minus 18 equal to 6. So at 6 users, this knee happens. So there is a homework for you to do on the asymptotic bound. Again, this homework is easy because all you have to do is fill in the blanks. You don't have to think about too much. It's already given, even the formulas are given. But I would appreciate if you read the book, because there is a lot more in the book. So there's another example. How many terminals can be supported on the time sharing system if the response time has to be kept below 100 seconds? So now they're not asking you the need, they're asking that we want to be less than 100 seconds. So you can do the similar things with this kind of formula, is that Rn has to be more than this, and response time will be more than 100 if n is more than 100. So this gives you, again, an approximate number that if more than 23 users come in, then the response time will be more than 100. So basically, in this graph, you just go to 100 here, and you are reading the number 23. And it turns out that both extremes here, this bound gives you very close to what you had. So this is, you see, the MVA, and these are very similar. So at 23, your answer will be very good. All right, so there is a homework again, something. That brings us to the end of this chapter. And what we have done is we have learned 6 laws. Actually, 5 laws and the bound, 1 bound. 5 laws and 1 bound. And by now, you should just get familiar with all the symbols. D for the demands, V for the visits, U for the utilization, X for throughput, Z for think time, N for the number of periods, and so on and so forth, because those are the ones that are here.